All right. Again, lovely to see you all on this wonderful, sunny and warm Monday morning. Um, yeah, so what we're going to cover today is our third and final formal language. So the aim is specifically to talk through all of the kind of grammar for modal logic, and then we're going to talk about constructing interpretations for modal logic. Now, I want to stress the notion of interpretation for ML is fundamentally different than interpretations for FOL. And it's really also important to note that calling ML an independent kind of formal language is being very generous. It is effectively just going to be truth functional logic with two non-truth functional operators. And in order to make sense of them, we're going to have to do something kind of strange. So the plan for today is to introduce you first to the concept that we want to try and capture. It's something we've talked about a lot already implicitly, and this is the notion of modality. So we'll talk about this just for like 5 minutes to kind of get a broad grip on this concept. And then we'll introduce ML, modal logic, this formal language. And here what I want to do is just tell you a little bit about the two new operators and about the kind of sentence construction rules for these. That will then get us to the third section where we talk about modal logic interpretations. So these interpretations are the ways that we can make ML sentences true or false. So they're going to be kind of similar to what we did with valuations for TFL or interpretations of a different kind for first order logic. Then once we have a grip on how these interpretations work, we're going to talk about various ML semantic concepts. We're going to get, again, kind of parallel stuff to the ones we had before, right? There's going to be something like being a tautology, being a contradiction, things like this. Importantly, modal logic is something where really we have modal logics. There's going to be 4 different systems I'm going to introduce you to. They all basically work the same way. The only difference is the restrictions that we'll put on how you make the interpretations. Honestly, the only thing that's different is the properties of a particular relation we're going to invoke here. We're going to have what we'll call an accessibility relation. And accessibility might have various features. It might be reflexive intransitive, it might be reflexive symmetric intransitive. Depending on what properties we give the relation, we get different modal logics. So that's the plan. I want to go through all of that. And then we'll talk about what's next for next week. So let's start by just talking about the very broad concept of modality. The idea here is that modality is literally modes of truth, ways of being true. But in most areas when we're thinking about modality, especially approaching it with logic, what we're interested in isn't about how things are or aren't, but whether they must be or whether they could be. That is, we're not interested in what's actually true. We're more interested in what could be true, what must be true, what must be false, what's impossible. And this is a concept that we've invoked a ton, right? Remember, at the very beginning, I introduced you to the notion of validity. And the core thing in validity isn't whether things are actually true or false, it's is it possible to make the premises true and the conclusion false? That's already invoking the notion of modality. So we're interested in things like this, not necessarily whether my sweater is in fact black, though it's very old, so really calling it black is being very generous. But it's this question of, right, does it have to be? Could it have been a different color? Is it possibly true that my sweater is gray? I mean, obviously it's false that it is, but could it have been? Is it possible? And you can play around with other stranger things, right? It seems given that this thing is a sweater, it probably has to be a sweater if it exists at all. Again, debatable. Maybe we could unravel it and turn it into a scarf. Does that mean it's the same thing, or did we kind of lose the sweater and now we have something different in its place? Notably, modal claims are ubiquitous. They're ubiquitous in philosophy, they're all over the place, but they're also ubiquitous more generally when we're constructing pretty much any kind of theory we want. Because what we're interested in isn't what's actually true, but what are the kind of limits? Like, what's the range of possibilities that we're dealing with here? What's the space of options? You get things in philosophy like ought implies can, right? That is, if you should do something, then it means that you must be able to do it. There won't be moral restrictions on you that you could not possibly satisfy. Or another one, the mind could exist separate from the body. This is Cartesian dualism. Right? Again, these are claims. I'm not interested in whether they are in fact true or false. Just note that they invoke this notion of possibility. Now, the neat thing is, there's a bunch of different flavors of possibility. And we can also think of different modes of modality. So we've already come across this idea of there being necessary truths, right? These are ones that are true and they have to be. It's impossible for them to be false. At the other end, you have things that are impossible, that is necessarily false. They're false and it's impossible for them to be true. The vast majority of stuff in the middle is things that could be true or could be false. Class started at 8:45 today. Thank God that is false, but if the schedulers hated us a little bit more, right, that could have been true. In fact, it was true last year. So again, you get this broad idea. And as I said, there's different senses of could, right? Different types of possibility and necessity. So at one end, we have what we'll call logical modality. Logical possibility and logical necessity. This is literally the broadest possibility, the narrowest range of necessities. That is, there'll be the fewest amounts of necessities that are logically necessary, and there'll be the most range of options that are logically possible. Because all we're interested in here is, does it generate a contradiction? If it doesn't generate a contradiction, then it's at least going to count as logically possible. At the other end, we have what we might call real possibility and necessity. Now, this is a very hard notion to characterize, but you can kind of get a grip on it by thinking about this is the notion of modality that invokes the way things actually are. So there's a sense in which it's possible for me to run, I don't know, let's say a 6-minute mile. Right? But that is certainly not in the realm of real possibility. You go put me on the track and force me to run a mile, I ain't doing it in 6 minutes. In all honesty, I probably ain't doing it at all. So real possibility is invoking the way things in fact are. Right? It's really possible that one of you gets up and sprints out of the door within like 4 seconds. Maybe, if you're in the back, right? But it's not going to be really possible if you're down here in the front, especially if you're in the middle, right? Because you got to get over everybody. Again, it's kind of building in these different actuality restrictions. Now, there's a notion here, don't worry too much about these different types. And in the middle, just to mention, we have this concept of nomological. Are people familiar with that term? Have you come across that notion before? So nomological means guided by laws. Nomological possibility and necessity is what's physically possible and physically necessary. That is compatible with or entailed by the laws of nature, whatever those are. So it's nomologically possible that any one of us could run, I don't know, a 4-minute mile. Right? It's physically possible. Though again, given the actualities of what our lives are like and how we live and things like this, it's probably not really possible. Right? It's compatible with the laws of physics, but it's not compatible with what's really the case. Again, rough and ready characterization. What's important is that these different senses of possibility will give us radically different spaces of options. And they stack. You tend to get a hierarchy. That is, everything that's logically necessary is going to be necessary in these other senses too. Another way to put it is, right, a tautology is still going to be nomologically necessary, because what makes it necessarily true has nothing to do with the laws of nature. It's just going to stay true all the way. On the flip side, right, what's possible in the real sense is going to be possible all the way up, because it's the most restricted kind of possibility. So as you start to widen out what you're holding fixed, that thing is still going to be possible. You can kind of think about it as you go down the hierarchy, you take more and more things as necessary, and hence your range of options gets narrower and narrower and narrower. Okay, but again, what matters for our purposes is just this general concept of how things could be versus how things must be, and trying to capture these notions. And it's notable that so far, we don't have the machinery to do that in any of our formal languages. We can talk about these being the case. We can use our meta language, right, English, but we can't express them in TFL. We can't express that in FOL. This is where modal logic comes in. So ML is going to give us the tools to express possibility and necessity in the formal language itself. So ML, modal logic, our third and final formal language, right? It takes TFL and everything there, and it adds two new operators, the box and the diamond. Importantly, these operators, strictly speaking, don't mean anything. They're going to be functions. Just like how, right, the little thing that looks like the A with a bar in the middle, conjunction, doesn't actually mean and. It's a truth function. It means whatever output it has. Right? It's a mapping from certain truth value inputs to a truth value output. It's designed to try and capture how we use and, but it doesn't actually mean and. In a similar way, these operators don't strictly mean anything, but we're going to tend to use them to capture the English concepts. So there's four kinds of symbols in ML. Everything that we got from TFL and our two new operators. And we, of course, can say an expression of ML is going to be any concatenation of these. But of course, not all expressions are going to be sentences. So what are the sentence construction rules for ML? Right? Well, let's get a run-up. First, let's talk about these operators. Again, the box and diamond don't strictly mean anything, but we will use them as an attempt to try and capture, respectively, necessity and possibility. So the box, if we attach it to a sentence, will tell us that that sentence is necessary. And similarly, if we attach the diamond to a sentence, it tells us that that sentence is possible. And notably, because these are in my sexy swash font, there could be negations in there, right? So I might have like box negation A. That's telling me it's necessary that not A is true. Again, you can start to see hopefully the idea. Now, the nice thing is once we have these, we can express the modal claims in our language, right? In ML. So I could say, right, take this sentence, possibly my sweater is black, something we could not capture in TFL by itself. Right? Well, we can express it with diamond B, where B is my sweater is black. Necessarily, if I exist, then I'm human. Right? We can put the box outside of the conditional. If I exist, then I'm human. And another one, right? If Socrates is human, then he's necessarily human. Well, here we can have, right, Socrates is human as our antecedent, and then it's necessary that he's human as our consequent. So this already tells us something about how these operators work. They're going to function kind of similarly, at least grammatically, as negation. You can stick them in front of a sentence, or they can be part of bigger sentences. But grammatically, they're going to behave just like negation. You slap them onto a sentence. So this gives us this sentence construction rules for ML, right? Every atomic sentence is an ML sentence, right? 2 through 6 are exactly like they were for TFL. The differences are 7 and 8. 7 tells us if you have a sentence, you can put the box in front of it. 8 tells us if you have a sentence, you can put the diamond in front of it. Now here's something to note. 7 and 8 also let us iterate modal operators. So if you have box A, and that counts as a sentence, then box A is going to count as a sentence. Or diamond box A. Yeah.
So let's say if you have a box or diamond, and can we do a negation of that? Would negation go after or before?
Absolutely. It could do either one, right? Because remember, the rule for negation introduction is if you already have a sentence, you can apply a negation. So if you have, right, box A, you can put a negation in front of it, according to clause 2. And once you have this, you can keep going. You could put, using clause 8, a diamond operator on that, right? Go nuts. This is a sentence. Now there's another question about whether it's true or false, but it's satisfying our sentence construction rules. So again, the thing to remember is the grammar for these is just like negation. You have a sentence, you can put these operators in front. That's the grammar for ML. Now, that's it, right? I'm not going to spend very long on the grammar here because it's just TFL. You know how to do TFL. The only difference is that we have these 2 new sentential operators. The interesting part is going to be, when are these sentences true or false, right? How do we know when the sentences are true or false? And this is where things are going to get interesting. So here's the big idea for modal logic. We're not going to be interested in sentences being true or false simplicator, right, on its own. Instead, a sentence of ML is going to be true or false at a world, or relative to a frame. So this means that truth is always going to be relativized. We don't say sentence A is true, we will say sentence A is true at world 1. This means that an ML sentence can be true at one world and false at another. And there's no conflict here because it's always relativized. This chair's empty, that chair's occupied. There's no contradiction because, of course, we're localizing it to chairs. It's the same kind of idea here. The truth of a sentence is going to be relativized. And then what we're going to be able to do, once we relativize truth, is we can treat our operators as something like quantifiers. So box A is going to tell us that A, that sentence, is true at every accessible world. Meanwhile, diamond A is going to tell us, right, that A is true at least one accessible world. But remember, right, when I say is true, that's actually kind of shorthand because it will be true at a world, right? So box A will be true at world 1 if and only if for every world 1 can access A. And diamond A will be true at world 1 if and only if there's at least one world 1 can access where A. So again, truth is going to be relativized to these worlds, and we can define the operators by what the worlds can see. So here's how we do it. We're going to have what we'll call an interpretation of ML. An interpretation of ML consists of a set of three things: W, V, and R. Let's talk about what the hell those are. W is a collection of possible worlds. It's got to be non-empty. That means there has to be at least one. Otherwise, we don't have an interpretation. V is going to be what we'll call a valuation function. More on that in just a second. And R is going to be the accessibility relation. And we'll have certain features for this accessibility relation. Let's go through these one by one. So, our collection of possible worlds. Right? What is that? Well, what exactly worlds are is a really deep philosophical question. But the nice thing is, we don't have to give a shit. Right? All worlds have to be are things that we can treat as representing sentences being true or false. So worlds could be lists of sentences. They could be giant space-time collections out there in the multiverse. They could be people sitting in chairs. They could be chairs. They could be pieces of chalk I've arranged on the board. Right? Worlds, what they are metaphysically, we don't care. What they are for us, for our logical purposes, is they are frames that represent certain sentences being true or false. And then what's the valuation function? It's going to be, as the name suggests, a function that assigns truth values. And it assigns truth values to atoms at the worlds. So for example, right, if we take people as worlds, we could then have S as a sentence, right? And this sentence, we will have a valuation function that assigns for me, right, the value true for sweater is black. For other people, like down here in the front, right, false for sweater is black because your sweater is bright red, right, and then green, and you see the idea. Again, what the worlds are don't matter, and what the valuation function is tracking doesn't matter. It just tells us, for this frame, this atomic sentence is true. For this frame, this atomic sentence is false, for all of the frames. Yeah?
In your examples of a person represents each world.
A person would be a world in this case, yeah, right? And then the function would basically be like, look at the person, is their sweater black? If yes, then S is true. If not, S is false at that world. Right? So I could be world 1, and then 2, and then 3, and then 4, and then 5 for each of us. And the valuation function would then give us either a true or a false for that sentence. The important thing, valuation function, yes, please. Yeah, good. So I changed S a little bit here, right? We might treat it as their sweater, right? So for me, it would be this one. For you, it would be yours, and so on and so on and so on. Yeah, so that's a slightly different example than what I have on the slide, but I think it fit better with the case we were talking about. Okay. Now the important thing, valuation functions do just like the name suggests. They're valuations. And remember, what were valuations? Valuations were assignments of truth values to atoms. So all valuations do is tell us whether certain atomic sentences are true or false. So that means that sentences that feature connectives, their truth value at a world is going to be determined by how the atoms work out at that world. So for example, right, if we have like S is this person's sweater is black, and H is this person is more than 2 meters tall, right? the valuation function for S conjunction H is going to look at me and be like, right? Because while S is true, H is false, I'm not 2 meters tall. Right? So the conjunction turns out to be false because of the assignment of truth values to the relevant atoms. Make sense? It's a quick and dirty example, but what will happen, it'll be a little bit easier once we start to see the diagrams. So the worlds are representations. They present to us certain things being true and certain things being false, certain sentences. Valuation function tells us relative to each world what sentences are true and what sentences are false at the atomic level. And finally, the last thing, a quick jump. I said this already. The valuation function for the connectives, it's going to work just like it did with TFL, right? Conjunction's going to be true at a world if both conjuncts are true. Disjunction's true at a world if at least one disjunct is true. The conditional works just like it was before, right? It's only going to be false at a world if the world makes the antecedent true and the consequent false. And the biconditional is true at a world if and only if the two parts have the same truth value. So the third element, the accessibility relation, is going to be the thing that determines whether the modal operator claims are true or false at given worlds. Because remember, the third element, accessibility, is effectively what worlds can the one we're looking at see? What can it access? Put another way, what possibilities are open to it? So the accessibility relation is a relation that holds or fails to hold between the various worlds that are in our system. And what they do is if the relation holds, it means that the world that you start in can access, can see the world that it's pointing to. So again, if we take all of us as the worlds, we can take accessibility as literally, who can you see? And then because you can see the other person, there's a sense in which the color of their sweater is accessible to you. So we can then define our modal operators. We can say box A is going to be true at a given world, if and only if every world that our first one can access, A is true. Note, A can be an atom, A can be a complex sentence, A can be another sentence with one of these modal operators in it. Similarly, diamond A is going to be true at a world, if and only if there's at least one world that our first one can access where A. So accessibility doesn't play in unless you have the box and diamond, because the rest of it, you can just basically ignore all the other worlds, just look at what's happening inside this one. But as soon as you start talking about possibility and necessity, you need to look at how can these worlds access the other ones? What arrows do we have? So here's the cool trick. We can produce diagrammatic ML interpretations. And in fact, this is what we're going to be doing. So these diagrams will represent worlds, and you can represent them an easy way. It's just as little boxes, right? And then you can write the sentences that are true in the worlds, the atoms that are true. So in this diagrammatic interpretation, we have two worlds, 1 and 2, and the valuation function assigns for world 1 true to A and true to B. And the valuation function for world 2 assigns false to A and true to B. So again, an easy way to represent the valuations here, you write the atoms that it's telling you are true in the box, and if it's evaluating it as false, you just write the negation in the box. And then you draw arrows, and the arrows indicate accessibility. So in this case, world 1 can see itself, and it can see world 2. And world 2 can only see world 1. So there's the arrow going both directions. So let's quickly just go through a couple things to see if we can read off from this diagrammatic interpretation what sentences are going to be true or false here, right? So let's take our first one, right? Is A conjunction B true at world 1? Yeah, right? The atoms A and B are assigned true in 1, so then the conjunction is true at world 1. How about A conditional B at world 2? So here what we do, you just look at the contents of 2, and you think about how the truth table for the conditional would go, right? And in this case, we have a false antecedent and a true consequent. So what does that then give us for the conditional? It gives us the true, right? False antecedent always gives us a true conditional. Yes?
What do we mean by world to pronunciate itself?
Good. So it's literally just we're defining a relation, right? So the nice thing is we can define the relation in any way we want. So all it means is that world 2 does not stand in the accessibility relation to itself. There's no kind of deeper, darker meaning. The thing to remember here is we are merely constructing models, right? It's not that there's some kind of weird, self-blindness, right? We're just constructing models. Don't read anything into it. Okay, so far so good with the first 2? So how about diamond A at world 1? Is diamond A going to be true at world 1? So in order to be true, there needs to be a world that one can access where A is true. Is there a world that one can access where A is true? Which world is it? Yeah, right? It can see itself. It's got the loop. And in world 1, A is the case. So world 1 can see a world itself where A is true. So diamond A is true at 1. Right? How about diamond negation A at world 2? So again, what's the rule? The diamond is true if and only if there's at least one world that 2 can access where not A is true. Can 2 see a world where not A is true? No, it can't, right? Because 2 does not see itself. So even though not A is true at 2, diamond not A is not true. Because it fails to be able to access a world where not A is true. It does not have access to itself. Does everybody see that before we go on? That is, if we get this, we're going to be okay. Yes, please.
How do we know what the word is itself? How do we know if the word is?
Good. So importantly, right, we're going to be generating these models. We're not kind of looking out in the world and asking, like, what's the accessibility relation? So in this case, the thing that tells us whether it does or doesn't is there a loop, right? Does the node have an arrow to itself? If there is no loop arrow, there's no access. Right? The arrows indicate accessibility.
If I see like the arrows and like the diagram, okay, but if I read the sentence, how can I say?
Good. So the important thing is they're not necessarily going to be anything, well, let's put it this way. The ML sentence itself will not tell you anything about what interpretation to use, because the ML sentence is going to be made true or false by an interpretation. So it's just like with the FOL sentences when we were constructing interpretations there, right? The FOL sentence didn't tell you anything about what interpretation to have. You had to think about, what do I want to do? Do I want to make this sentence true? Do I want to make this sentence false? So in this case, what we're doing, much like what we did in the initial things with interpretations for FOL, is we're given an interpretation and we're seeing what comes out in this one. What we're going to build to is constructing our own. So this is making sure we've got that process down first before diving into the deep stuff. Good. Okay. So again, in this case, diamond negation A is false at world 2 because it cannot access a world where negation A is true. Here's an interesting one. Let's take the conjunction of box B and box A. Let's just try box B first. Is box B true at world 2? Right? So, when is box B going to be true? It will be true if and only if every world that 2 can see is a world where A is or where B is true. Right? Is every world that 2 can see a B world? Yeah, because the only world it can see is 1, and B is true in world 1. Yeah? So, box B is true at world 2. How about box A? Same story, right? Exact same story. Because every world that 2 can see is an A world. So is the conjunction true or false? It's true, right? Because both conjuncts are true at world 2. Here's a fun question. Is this sentence, the one at the bottom, so we've said it's true at world 2, is it true at world 1? Is box A conjunction box B true at world 1? No, right? Both conjuncts are going to be false. Why? Because if we look at world 1, just take box A. Is box A true at world 1? In order to be true, it must be such that every world 1 can see is an A world. And it can see itself, which is an A world, but it can also see world 2, which is not an A world. So at least one of these conjuncts is false at world 1. So this sentence, while true at world 2, is false at world 1. Okay. Before we go anywhere else, what questions do you have for me on what we've done so far? Yes, please.
As far as we are concerned, like, you always be presented with the diagram and things.
Cool. So there's going to be 2 kinds of things. One kind of question is, I will give you a diagram and ask you to tell me on this diagram what sentences are true or false. And the second one is going to be, I'm going to ask you to construct your own to show me certain things. That's what we're going to talk about in the next section. Right? But again, first we got to know how to do this, because if you don't know how to read it off, you're not going to know how to build them. Yes?
Yeah, well, it's one will see another one. Is that because it's read by the second?
It's just literally what arrows we draw, right? What accessibility relations we have.
Like, why did you draw arrows in what rule?
Good. So this is an interesting and heavy kind of question, right? One of the things we're going to get when we talk about the different kind of modal logics, and we won't really talk about it a lot because I'm just interested in making sure we understand the systems, is what philosophical or otherwise motivations would you have for invoking this kind of web of connections versus some other one? Right? And that's a kind of thorny question. My focus is really, let's get how to do the system right, and then we can think about when and where to apply it. It's a good question. Okay. Anything else? Other stuff on this general idea? Is again, the things to remember, if there ain't no boxes or diamonds, whenever you're looking at a given world, it's just like TFL. Just treat it as a given valuation. If there are boxes or diamonds, remember that the box means everybody it can access, and the diamond means at least one world it can access. Okay. So an ML interpretation consists of three elements: the worlds, the valuation function that tells you which atoms are true and false at given worlds, and the accessibility relation that tells you what worlds can see each other and how. Complex non-modal, that is, sentences not featuring box and diamonds, are true at a given world just as they were with TFL. Modal sentences, the one with the box and diamonds, are going to be driven by a combination of that basic valuation stuff and accessibility. Here's the cool thing. If we change the accessibility relations, we're going to get radically different modal truths. So this brings us to the ML semantics, and this is what we're going to talk about after the break. Because we're going to get 4 different modal logics, 4 different kind of modal systems. The first one is going to have no restrictions on accessibility. And then we're going to build in different properties. So we have no restrictions. The next one is every world has to see itself. The next one is accessibility needs to be both reflexive and transitive. And finally, the fourth system is it's reflexive, symmetric, and transitive. And what you get then is every world can access every world. And there's a pretty good reason to think that if we're modeling possibility and necessity, this is the kind of view we want. But again, if we're thinking temporally, you might want just the weaker one, reflexive and transitive, not symmetric. But again, stuff to think about. So what we've done, right, is we've set up the basic language, introduced the 2 operators, and we introduced the real basics of these ML interpretations. In particular, when our box sentence claims true at a world, when our diamond sentence claims true at a world. That's the stuff that's important for us going forward. Okay. So it's 28 by my clock. We'll take a break to 40. Is that okay with everybody? So 12 minutes or so. And we'll come back and we'll talk about these semantic concepts and the different systems. Nice.